All right. Okay, let's repeat that then. We have what's the strongest force? They're all weak intermolecular forces. What's the strongest one? Right. So, okay. Hold on. So we have. Don't write this. Just pay attention. We have electrostatic, and we have coulombic. Right. Those basically mean the same thing. What crystal structures use those? Ionic and metallic, right? Those are extremely strong. Those are actually classified as bonds because they're so strong, but they're really technically forces, and they're kind of a separate. I'm just explaining that these are separate. When I say forces or weak forces of attraction, I'm not talking about these. So between molecular substance, inside molecular substances, so between molecules, you have weak forces, so hydrogen bonding, dipole forces, you have induced dipole, you have dispersion. Those are basically the four main types. Hydrogen bonding, dipole interactions, induced dipole, London dispersion forces, and then you have kind of a special one called ion molecule, or molecule ion. Let me just make sure I'm not forgetting one there. I think that covers it. Again, I sometimes do too much off the top of my head. I gotta check myself here. Ion molecule sometimes is called ion dipole. So those are these are the four forces involved with molecular. This involves ionic, which involves this, and a polar substance, which is the dipole, so molecule. So I'll talk about that in a minute. What do you need to know about this? So hydrogen bonding is H with NO or F. So the classic ones are H2O, HF, and H3. Those all have hydrogen bonding. Dipole would be polar substances. Dispersion is essentially nonpolar. But everything has dispersion. All molecular, whether it's polar or nonpolar, everything has dispersion. Okay? Induced dipole, that typically is when you mix polar and nonpolar. But induced dipole is also kind of like dispersion. I'm going to give you an example of each one here in a minute and draw pictures and dotted lines. But induced dipole is how dispersions work. So I'll explain that kind of like together. Dipole is really just polar substances that don't have hydrogen bond. So these two forces are exactly the same. It's just this is stronger because NO and F have really high electronegativity. So they explain the exact same way, partial negative and positive on a polar molecule. It's just this one's special. And some of this should be, you've heard it many times in Regents and in here, so you should be good with it. All right. So let me give you an example. I'll draw a picture of each one here, explain how they work, and then we're going to do the lab. Okay. So I can erase this, right? Okay. All right. So hydrogen bonding. I mean, I feel like we don't need to do this, but I'll do it one more time here. So if we have NH3, well, yeah, I'll draw it out. NH3, you have your three H's, and then you have your lone pair. One of these H's will be attracted to the N on another ammonia, and that right there is your H bond. Last night I went to my aunt's house because my cousin, my aunt's daughter, her daughter, so my cousin's daughter, is my goddaughter. I'll say daughter one more time. And we went to her house because it was her birthday on the 7th, and my daughter's birthday was on the 29th, so we celebrated both of them last night. And my cousin's daughter is taking biology, but she was learning about, so I was talking about science at dinner, obviously. And she was talking about how they learned about, bonding and hydrogen bonding, and I was like, everybody stop. It's not a bond, it's a force of attraction. And she was just kind of like, okay. And I'm like, trust me, it's a force, not a bond. I don't care what people tell you. So, and then her brother, he's the kid who goes to CBA. I think I was telling you about that. He's in chemistry, and we were talking a little bit about that, but then I stopped. I said, I don't want to be that guy. I don't want to be the guy, and they're like, oh, here he comes for Christmas or whatever, and he's going to talk about chemistry again. So I'm not that guy. So no, I usually go the sports route because he played football and he does track and she does track and gymnastics. My other, so we'll just talk about sports. That's more fun. All right, moving on. Anyways, that's an H bond. That's the point of that story. Okay, what's next on the list? Dipole, right? So if we take something like PCl3, okay? PCl3 is attracted to another PCl3 because your dipole would be going this way. This side of the molecule would be partially negative. But again, you know, I showed those images on the molecule simulator there, and they kind of draw those big bubbles. So like this whole section would be partially negative, and then this would be partially positive. So it isn't like just that Cl. It's like there's a distribution of negative charge on this side, distribution of positive, and the colors on the simulator, this would be like, you know, I always forget, red, this would be red, and that would be blue. But anyways, this is dipole because it has dipoles, so it's attracted to another PCl3, and again, it's the opposite charge. So there's your dipole interaction. It's literally the exact same thing as hydrogen bonding, but it's just not with H, N, or F, okay? So that's the difference. And again, this should be you should be like, okay, I get this. We've seen this a million times. All right, so that's dipole. It has to be polar. This doesn't form with nonpolar, not dipole interactions. Okay, so there's your dipole. Oh, and before I move on, one thing I do want to make sure you understand is if you have something like, what's this called? Who's got it? Propane. Good. All single bonds, alkane, propane. This hydrogen, let's say, if this was drawn on, don't draw this, just watch. If this was drawn on a test, and this could be a classic question, which of the following shows hydrogen bonding? And let's say this was a multiple choice. This was one of the choices. Some of you might think that does have hydrogen bonding, but it doesn't. So what's the problem? And I want to make sure I spell this out, because I don't make this clear in Regents, because they don't really have to worry about it, but you guys do. They'll try and trick you. This is not hydrogen bonding. So if this force actually did exist, which it really does, water and propane won't mix very well at all, but if it did, it would be called induced dipole. We're going to get to that in a minute. This is not hydrogen bonding. Why? What's the definition? It's hydrogen attracted to an N or F. Is that not a hydrogen? It is. Isn't that an O? It is. So what's the problem?
O already has hydrogen bonding.
Good try. I'll give you another. Here we go. Just want to make sure I'm on the screen there. Does anyone? I'll be impressed if you know the name of this one. What's the prefix for two carbons? F. Does anyone know the NH2 group? It's an amine, so ethanamine or ethanamine. I can't say that, right? Ethanamine. So this, stay with me here. Too bad Chi-Chi's not here, but I'm recording. Plus, Luke, you're going to memorize everything word for word, right? Okay, this would be the answer. That's hydrogen bonding, that's not. What's the difference? Right, that's the key. And if you need to write it down, maybe not, maybe just seeing it, listening help, you know, you can get it. But if you need to write that down, then write it down. If the hydrogen is not bonded to an N, O, or F, it doesn't work. So this is not classified as hydrogen bonding, but this is because that's an N. So in Regents Chem, these are the only three they will ever see. I can be pretty confident with that statement. So that's because H is bonded to an O, to an N, and to an F, and then it's attracted to another one in another molecule. AP, it's not going to be the case. They're going to try and get you. All right, again, that's not hydrogen. This is, it needs to be bonded to an N, or an O, or an F. So if this was an O, then it would work. Obviously, it couldn't be an F, because F only makes one bond, but just want to make that clear. Okay. I think there's a question like that on your midterm. So now you're ready. You just have to remember it. Oh yeah, it's basically like a full AP test too. Yeah, the problem is they're not giving us any. They used to give AP classes special like time to do that, so we're gonna have to use class time. And I have some other ideas, so we'll talk about that later. What's next? Hydrogen bond, dipole, induced dipole. All right, I'll do dispersion and induced dipole at the same time. All right, so let's say. Okay, so iodine solid. If we were to put this in water, all right, so if we put iodine in water, and I asked you, will that form a solution? You would say? Answer like how you, like what you know. Don't overthink it. Would it dissolve or not? See, this is the AP effect. You start learning so much that you second guess everything, and then simple questions you're having trouble with. And I'm not saying that to make you feel bad. It's just that happens to you. You get all this in your head, and you're like, I'm trying to figure everything out. What's the bonding here? Polar or non-polar?
Non-polar.
Non-polar. What's this?
Polar.
Polar. So will they dissolve? No. Like dissolves like. You can use the phrase, you just can't write that. You need to explain more. This uses dispersion. Okay, and this uses H bonds, which is basically dipole, just super strong dipole. So if their forces are the same, they will dissolve. Well, these don't dissolve. But what if I told you on an AP test, or if the AP test, said, guess what? I2 is slightly soluble. So the question would say, explain why iodine, or how iodine is slightly soluble in water. So I2 is slightly soluble in H2O. Explain. And they would say, explain using your knowledge of AP Chem and what else? They would say something like, using bonding and forces of attraction. They would kind of lead you on what they wanted you to say. But the answer is induced dipole. So what happens is you have iodine molecule. It's attracted to other iodine molecules through dispersion. Bell's gonna ring real soon. Let me finish this thought, then we'll take a break. And the reason this occurs is electrons are moving, and dispersion forces are caused by electron movement. At any given time, so just stay with me until I'm done with this. Any given time, all the electrons may be on the left side of these molecules. So all the E minuses would line up over here. So this side would be partially positive, this side would be partially negative. This happens constantly with nonpolar things. Electrons are always moving around. So at any given point, this happens. So when you have a positive, negative partial charge, that's called a dispersion. That's also called a temporary dipole. So dispersion uses what's called a temporary dipole. Temporary dipole. And temporary means it doesn't last very long because at any given moment, all the electrons can move back. So if they all come to this side and it repels the negative, that force is going to break. That's why iodine is so weak. It can sublime very easily. Most gases are nonpolar because of that weak temporary dipole. If that was permanent, there'd be solids and liquids and no gases. So this is called temporary because of the motion of the electrons. Well, if you put I2 in water, the exact same thing happens. At any given point, we know water is polar, dipole going towards the O. At any given point, this can happen. So if you put something nonpolar in water, and it happens to slightly dissolve, which it does. If I put iodine in water, there's like a very, 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 very faint, like brownish yellow tint That's because some of these will slightly dissolve. And the reason is this. Because it has dispersion, which deals with electrons just kind of moving around within the molecule, and again, because they're shared equally, they can kind of move around wherever they want, the electrons, this can happen. So partially and temporarily, because this is very, very negative, I guess I can say it that way. Because this has a dipole, when this comes near the iodine, it actually encourages the electrons to kind of move to the other side, so it induces a dipole. So whenever you take something polar and bring it near nonpolar, it induces that. It's kind of like this, except it's because the polar is kind of forcing it to do it. So again, this is called an induced dipole. I'm trying to be clear, not be confusing. I'm just trying to explain both at the same time. Dispersion happens all the time between nonpolar because electrons are moving. This can happen because the polar molecule kind of forces the issue and sort of makes it temporarily have a force. So again, this induced dipole is temporary. It's not always going to stay. It's much weaker than an actual dipolar hydrogen bond. So that's what induced means, is when you take a polar, put it in contact with a nonpolar, and it kind of forces the issue there. That's called induced, but that only works the more polar this is. The more polar this is, the better this will work. Okay, so again, two nonpolar, it's called dispersion. Polar nonpolar is called induced. All right, and I'll stop for a few minutes here, take a break, and then we'll come back, wrap it up really quick, and then get going on the lab. Obviously, we're going to have to use time tomorrow, but that's okay.